Today, we're gonna start a new chapter about the duality between mixed moments and coefficients. So you will use this notation. So suppose P and X is a monic OPS. Okay, and we will write each polynomial the usual way when we express a polynomial, and we're gonna say that the coefficient of x to the n is nu n comma k. So this is nu n comma k, and we will show so for this is how we expand a polynomial as a linear combination of the standard basis vector. So of course the coefficients are unique in this way, but we can also express, because they also form a basis of the space of the polynomials, we should also be able to write x to the n as a linear combination of pk. Okay, and we will show that the coefficient in this case is mu sub nk, where mu sub nk is the mixed moment that we defined in this way: x to the n pk x over pk x squared. This is the mixed moment. And we have a combinatorial interpretation of this mixed moment using Mochkin path, starting from 0, and here is n, here this is k. This is the generating function for all Mochkin path. Okay, we proved that before. So so in this chapter, the main purpose of this chapter is to study the duality between the coefficients and the mixed moment. Because of these two inequalities, they are naturally dual to each other in some sense. So we will study them using combinatorics. Okay, and we will also later in this chapter we will also study some special case of this duality, and then we will get some well-known dualities between some results in symmetric functions, like the duality between elementary symmetric functions and homogeneous symmetric functions. But we will see them later. All right, so let's begin with the first chapter, section 6.1, mixed moment and coefficients. Okay. So as always, we will assume that this is an OPS, and we will assume that they satisfy this three-term recurrence for some Bn lambda n, right? And also this mu and k is the mixed moment defined in this way, but we also have a combinatorial model. But we know that this is a generating function for all Mochkin path, which I'm gonna denote by Moch n comma k, weight of pi, where Moch nk is the set of Mochkin path from 0 to 0 to n comma k. So it's like 0, 0, and this is k, something like this. Okay. And just to recall, if we have a height I, the weight must be lambda I, height I, the horizontal step must have bi, and every up step has weight 1. Yeah, this is something that we proved before, right? And we will see things like this in this chapter for focusing on the connection between mixed moments and coefficients. So first, let's prove this. So first, proposition. This is the statement that I wrote. So if we write xn as a linear combination of pk's, then the coefficient is exactly the mixed moment mu and k. Proof. Proof is actually quite simple. We know there must be such an expression. So let's say sigma and k. You can always write in this way uniquely because they also form a basis. Okay. And now multiply p to the kx, a piece of kx, the usual technique that we extract the coefficient. Multiply this and take the linear functional, then what we get is L of x to the n pk equals, because we multiply pk here, only this term survives and the other terms all vanish. So we get sigma nk L of pkx squared. But of course, this means that sigma nk equals L of x to the n pk over L of pk squared, which is exactly what we wanted. So that's the proof. Proof is really simple, like that. Okay. Now what? So let me write this formula, this expression next to each other. So we have this. So we have this and Pn. This is just a definition. X to the k. Okay. We have two equations like this, right? And then we know that x to the n, both sequences form basis. Both are basis of polynomial space. Right? So this that means these two equations can be written as we saw this before. Mu nk p0 p1 dot dot dot, and also if you write using matrix equation, we get something like this. So these two are change of basis matrix, right? That means we have matrix identities. We have two matrix identities. They are inverses of each other. That means if you multiply the two matrices, so nk both 0, so the infinite matrix, you can think of them as infinite matrices. This is the identity, and also you can change the order, so it must still be the same. So we have two identities like this, okay? But if you have an identity like this, just let's compute like n comma m entry. Then this is equivalent to saying that for any nm, for fixed n and m, sum over all k, mu nk, nu km equals delta mn. So they are equal to 1 if both n is equal to m and 0 otherwise. And also from the other equation we get n k mu km equals delta nn. So we have identities like this, all right? But if you think about this, these are interesting combinatorially because we have a combinatorial model for this, the Mochkin path generating function. And we also have a combinatorial model for this because we have a combinatorial model for this using Favart tiling. That means we can extract we can get also a combinatorial model for each coefficient. So we have a combinatorial model for this and also for this. That means there must be a way to understand this completely combinatorially without using any orthogonal polynomial or the basis of linear vector space and anything like that. It has completely combinatorial meaning, and our goal in this chapter is to prove both identities combinatorially without referring to any known knowledge in orthogonal polynomials or vector linear algebra. Okay, but these proofs will be quite similar to the proof that we saw before when we proved the combinatorial model for mu and k. If you remember, we found the sign reversing involution when we have a combinatorial model using Mochkin path and Favart tiling. I'm going to review that combinatorial proof anyway, so it's okay if you don't remember them right now. In fact, the proof will be simpler than the previous proof, so it should be not too difficult. All right, so that's our goal. So the next section, combinatorial proof. Of duality. By duality, I mean an identity like this. So these two, we can say that these two quantities are dual to each other in this way. So, and also they are the equivalent statement. And the thing is, we will prove this in a slightly more general setting without assuming that they are coming from orthogonal polynomials. So, right, one thing is, if we have orthogonal polynomials and if you define mu in this way, we have to assume that this is non-zero, because if this is orthogonal polynomials, the three-term recurrence coefficient must be non-zero. The lambda, b could be 0, but lambda must be non-zero. But we will not worry about that situation, and then just define mu just combinatorially. So define. So let's say Bn lambda n be any sequence. So any sequences. So lambda n may be 0. We don't care. So it's not, they are not the three-term recurrence coefficient from orthogonal polynomial. It can be anything, okay? And then we'll just define mu n k to be the usual definition of the Mochkin path moment. Wait. Of course, if they came from orthogonal polynomials, then we know that they are mixed moment. But we don't worry about that. We take this as a definition, and then we will prove it. And that will be more general because we can put lambda n equals 0 at the end. And also, nu and k, just a definition. T, this is actually the Favart tiling model, combinatorial model for the coefficient of orthogonal polynomial. So let me remind you the definition here. So here, ft n sub k is going to be the set of Favart tilings of one times n board with exactly k red monomials. Yes, I think we need some definition example just to recall you what tiling is. So 0, 1, 2, 3, 4, 5, 6, 7. I think it's too long. So okay, so for part tiling we just label 3, 4, 5, 6, 7. So this is a Favas tiling. Sorry, just a one n times 8 board, and I'm going to so we have there are 3 types of tiles, like black domino and black monomino like this, and red monominos. So there are 3 types of tiles like this. There are no red dominoes. There's only one type, so black. And then how did we define the weight? So domino has lambda weight, but lambda, the weight, the subscript will be the largest integer in the domino, where the integers are it starts from 0, 0, 1, 2, etc. And this will have weight, this is minus and B3, minus B4, minus B7. And every red domino has weight x if we define weight of t. But if you remember, weight prime means that we just forget about all the weight of x's. So it's going to be this. So here, if we say t, then this is a Favas tiling 8, 3, because there are 3 red monominos, and the weight prime will be the product of this. So lambda 1, P3, P4, P7. So no x's there. That was our definition. And our before we proved that this is coming from the three-term recurrence. This is the weight generating function for all Favas tiling. But now, if you collect x to the k, then that coefficient must be this. That means you only look at those in this Favas tiling, because the number of red monominos will be the how many x's you have in the tiling. So anyway, you can take these as definition. So no orthogonal polynomials right now. Okay, and then we're gonna prove this theorem, that identity nu and k, mu k m equals delta n m. So n m are fixed integers, non-negative integers, and we have this. Okay. Oh, by the way, before proving this, let me tell you a little bit of some observation. Note. What happens if n is less than or equal to k? Then what is mu and k? Oh, this is the general Mochkin path that you want to go from. This one is n, this is k. But if k, what happens if k is larger than n? So k is somewhere over here, n is shorter. There's no way you can go from here to here using only the 3 steps, because even if you use only up steps, you will only go up until the height n. So this will be 0 because the sum is empty. Empty sum is a 0. Okay? And also, nu and k is 0 because the meaning of this is that you have n boxes, but you want to have more than n monomino, red monomino. It's impossible. So this is also 0. This is also 0 if n is larger than k. Therefore, so here, what I want to say is that in the proof, we may assume n is greater than or equal to m, because otherwise n is less than m. The product of these two is 0 for every k, because if this is non-zero, that means n is greater than or equal to k is greater than or equal to m, right? That's the only way that you can get a non-zero term. Non-zero term only occurs. Okay, let me write it, and I think it says this is non-zero. Okay, I think this is better. This is non-zero if, only if, right? So that, in other words, if we have this, there is no k that makes this non-zero. That's why. So this will be 0, and of course this they are different. So this is 0. So this is true. So we will only consider this case. Okay. Now the proof is really similar to the proof that we had before. So let me just to remind you how they look like. Let me just show you some diagrams. There should be some diagrams. Yeah, something like that. You remember, at least you remember that we had something like that. We will use the combinatorial models like this. It's going to be quite similar to this. Actually, it's simpler because we have less cases. So in fact, this is really a special case of the previous proof, but we will do this anyway because it's a good time to review that algorithm. And also, the second identity is not a special case of the previous argument, so it's good to compare the two methods. But anyway, let me start explaining the proof. And so let X be the set of okay, let me just write it this way. X equals set of pairs where T is a Favart tiling and pi is a Matchkin path. Where K is something between M and N. Okay, because of the assumption, we can define this way, and it's non-empty. And eventually, we will find the sign reversing involution here, and Y will be a set of elements like this, where let's say the same condition. Let's say is in X, where T has okay, let me just explain using this, where T is just red monomials only, all red, and pi up steps only. Okay, this is, so actually there is only one at most one such pair, or could be 0, empty. So what happens if so we assume that N is greater than or equal to M, right? What happens if N is greater than M? So this means that because this is in X, the size must be N, size of the Favart tiling. And okay. So this is N. Everything is red monomial. That means this must be N as well, right? So this is actually maybe I can explain. explain a little more. This is actually, this must be f t n n, and this here, this is k, and this is m, right? But because if we have only up steps, this must also be m. So this must be a much mm. But these two must be the same, so it's impossible if we have this. So this is mt. But if n is greater is equal to m, has a unique pair, right? Like this. So there is such a thing, and this will give weight prime. What is the weight in this case? Up steps only, so the weight is 1. Only red has weight 1, so the weight is 1. So if we can find a sign reverse involution, on say a phi x to x with fixed point set y, we are done. Because because this part is, maybe I can just copy this. This is really the generating function for because this is the generating function for all this. Right? This is equal to this because this corresponds to this corresponds to this. So if you can find the sign reversing involution of this with only fixed point y, then this will be equal to this, but this will be nm. So that's why it's enough to find the sign reversing involution like this. So this is what you need to do. All right. And the setting is really similar to before. So if you see this map, you will remember the bijection. All right. So this is our goal. So to do that, we need to do some setup. So suppose we have this. We have this, where T is in Babar tiling NK, pi is in Mochkin path Km. All right. Suppose that we have this, and we will find the corresponding object T prime. So we define this, the corresponding T prime pi prime, by modifying these two objects a little bit. All right, so it's best if I explain this using a diagram. So suppose that we have things like this. By the way, I'm gonna write pi s1, s2, sk, sequence of steps, because this is the length, so there are k steps. So let's write pi in this way. Okay, and I'm going to give you an example. So, example. Pi looks like this: up, up, horizontal, down, up, up. So pi and t. 0, 1, 2, 3, 4, 5, and 6. And then this is monominal black, and all The rest are red. Like that. So where is this? This is in Fava tiling. The size is 7. And how many red squares are there? 6. Okay, 7.6. And this is, where is this? This is in Marchkin path. What is the length? The length is 1, 2, 3, 4, 5, 6. And what is the final height? K, 3. M, sorry, this is M. So K, they are the same, so this is a valid object here. So you have to check that these two are equal. The length must be the number of red boxes over here, all right? And we are gonna define two quantities. So here, U is 2, where U is the maximum number of up steps at the beginning. Okay, so in this case, U equals 2. And A is the maximum number of red monomials at the beginning. Okay? And so what is the weight here? The weight here is minus P3. And the weight here, let's look at the weight of this step. This is B2, all right? This is B3, all right? Let's make it. So let's see what we can do with this. So the idea is change this into something over here. So remove this and then change this to a black monomial. Then this will become minus B2, right? And this disappears. The weight is exactly the same except the sign. So it's going to be a sign reversing involution. So I think I need this. So case 1, we will compare A and U. So case 1, let's say A is U is less than A, just like this, Okay. So in this case, remove this step. In this case, actually there are two cases. So the A plus first step is this, right? U plus first step is this. So there are two cases. Case 1-1, as U plus first step is horizontal. Or case 1-2, U plus first step is a down step. So in this case, we define pi prime to be pi except pi minus SU plus 1. So just remove this. Okay? So what happens is, I think I can just use the whole screen, whole page. So pi prime is the same except I just delete this, okay? And then of course I have to move this over here, like that. This is pi prime. And what about t prime? So make this, make the U plus first monomial black. So this is the red, actually red into black monomial. So here change this into a black monomial like this, and then we get weight minus B2. So this weight disappears, but we get this with minus sign. So there will be a sign. This will be a sign reversing map. Let me now just delete this. So A is now A. This is A. U prime is still the same. A prime is now decreased. So in this case, actually A prime is always less than or equal to U prime. Here A is greater than U. Let me change the order so that we have the same order here. So U less than A, then in this case U prime greater than or equal to A prime. Like that. All right. Now case 2. This is U. Okay. Maybe I can explain somewhere here. This a little down over here. So case 2. So it looks something like this. I'm gonna give you an example. Pi equals up, down, up, and P is like this. 1, 0, 1, 2, 3, 4, 5. And then this is red, black. The remaining are red. So what is U here? U is 2. Right? And what is A? A is 3. So again, U is smaller than A, but this step is a down step. Okay? In this case, we're gonna delete this peak. So in this case, I can just pi prime, delete this peak. So if the weight is minus lambda 2, or the weight is minus B3. So if you delete this, you get just 3 up steps like that. Okay? You collapse this into a single dot. Here you collapse this to a single dot like that. And T prime is almost the same. Except because we deleted 2 steps, we have to change 2 red dominoes so that we have the same k numbers. So these 2 will be changed into a domino, black domino, of course, black domino like this, and the weight is going to be minus lambda 2. So this is the map. Okay. This is actually the same thing that we did before. So I'm not going to go into too much detail, but hopefully you will remember. Okay, so this covers case 1. What about case 2? U greater than or equal to A, the other case. But we also have to consider the case that this is not equal to N. That means there is something that's not equal to a red. It's not everything is red. There is something black, domino, monomial. And these will be corresponding to things over here, so we will map just like that. Okay, so in this case, similar to case 1, except we do the opposite, go the reverse direction. So for example here, in this case, if this step, if this is a black monomial, then we expand this into a horizontal step, okay, and then change it into a red monomial. And if this is a domino, we insert up and down, and then change this into a red monomial, like that. So it's exactly the opposite thing. All right. And what about the remaining case? So we covered u less than a, u greater than a, but this is not equal to n. So the remaining case is u greater than equal to a, but this is equal to n. What does this mean? But this means, but actually, in this case, u, what is u? U is the number of steps at the beginning, of steps. So this is always less than equal to, what is that? Okay, let me just write this. Why is this less than k? Oh yeah, of course. K is the total number of steps. So this is less than equal to k. U is just only the number of steps at the beginning, so it must be less than equal to k. But this is our assumption. Our assumption is here, assumption. But because of this, we get they are all equal. Okay. But in this case, we have only up steps. This is u, this is u, and also this is k. Everything is equal, so this is n or k. So it's up steps only. So pi has only up steps, and a is equal to n. That means t has only red only. So this means that we have this is element in y. So in this case, define this to be a fixed point. Actually, this is in y, right? So this is a sign reversing involution. Only in the case 3, we have fixed point, but otherwise we have cancellation. And of course, this may be empty. There may be an empty case for this, if n is different from n. But if they are equal, we have only one term surviving. So that's the proof. Okay. All right, so that is the proof of this duality. So let's see. We have 2 dualities here, but we proved this first. Now we will prove the other one. All right. The other is similar but slightly different. Summation mu n k nu k m delta n m. Again, we may assume n greater than equal to m, otherwise both are 0. And define x to be, so the idea is really almost the same, except we have to do from the beginning, from the end, starting from the end. Instead, because here we looked at the first the maximum number of steps at the beginning, but we will look at the maximum number of steps at the end. And so slightly different things, but the idea is quite similar. And also, I'm gonna define t, where now I'm gonna put, the order doesn't really matter, but for some reason I had to change the order. But, pi is Motzkin path, nk, and t is Favart tiling km, where k in this range. Okay. And similarly, we want to define y. The element in x such that again pi is up steps only, t has red only. Okay. Then the same reasoning shows that this is empty if these two numbers are different, and only one there is a unique pair if they are equal. So the left hand side is again mu nk. By definition, this is really the sum over all pi t, weight of pi, weight prime of t. So our goal is claim, or there is a sign reversing involution and rate preserving involution phi with fixed point set y. And it's enough to prove this claim as before. Okay. All right. So how can we prove such a thing? So suppose just consider one such an element, pi comma t, where pi is in from of n comma k, t is Favart tiling in k comma m. And because we want to consider steps from the end, let's write pi s1 dot 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 sn in this way. There are n steps, but I'm gonna write the steps backward like this. Okay. And right. Again, I'm gonna explain things with examples. Example. So it's more complicated. One up, 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 down, down, up, horizontal, up, up, up. This is pi, and t is going to be 0, 1, 2, 3, 4. And this is black and the others are all red. And define u to be the maximum number of up steps at the end. So u equals 3. And a is, before is a maximum number of red monomials at the beginning, but it will be things at the end. So a equals 4. We do the same thing except we start from the end. All right. And the idea is okay. We define. I think we need the space. So define V as follows, and the case by case. Case 1, n u less than a. So the conditions are slightly different because because of the nature of this map, I would say. So, all right. So in this case, the first, from the beginning, I'm talking about from the beginning, from the end. The first non-up step is a horizontal, right? In this case, U is less than or equal to A. The first first non-up step is a horizontal step. Okay, so there are two cases. SU plus 1 is horizontal, and case 2 is, of course, SU plus 1 is down. So in this case, S1, S2, S3, S4, so this is SU plus 1, which is a horizontal step. Okay. In this case, but before, before we collapse this, but we don't collapse this. But let me tell you the difference here. So maybe I can show you what is N here, maybe here. What is N? N is this number of steps, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is K? Is the height. So it's like 1, 2, 3, 4, 5. And this must be K. This must be K. K must be the number of the size of the Fabara tiling. Okay. And M is 4, so number of red monomials. So note that the number of red monomials is always the same. It doesn't change. So this doesn't change, and number of red monomials doesn't change. That means you cannot simply collapse this because that will change the number of steps. We want to keep the number of steps. So instead of collapsing this, we're gonna just change this into an up step. Change this into an up step. So that means this becomes an up step, like that. But of course, we will have to move this up as well. So this becomes this. So change this to up step. And what about, we also have to change something over here. But you see, the height, ending height is increased. But the ending height is the size of your Fabara tiling. That means you just don't change just one monomial into a different color. We have to really create a new monomial because we want to keep this the same as the length over here. So in this case, this is a U plus first step. So after U red monomials at the end, we're gonna insert black monomial. So insert. So okay, I think I have to redraw. So these are all shifted, but this is inserted. Okay, we insert something right. So what is the weight? This is weight B2. This is exactly the weight of this. And this is minus B0, minus B0 still stays the same. So here we lose this weight here, but we get that weight, but we have minus sign. So it's a sign reversing, weight preserving. All right. And what about the second case? Or I think I'll explain the. Oh no, actually I'm gonna use a different, just a new, completely new example. 1-2. So pi is up, 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 and down, horizontal, up, down, up, up, up. So this is pi. Oh, sorry. T 0, 1, 2, 3, and 4. So what is A? A is, U is 3. Here U is 3. A is 4. Okay. And this. So we look at this step. This is the U plus first step is a down step, right? Then the idea is similar because we don't want to change the number of steps. Only thing that that's possible is to change one step into another. So, and as before, we just change this into an up step, like this, up step. And then, of course, we have to make this over there. So U may change, doesn't matter. U is now 5. U prime is 5 now. And again, this must be the length. So because -1, height -1, this will contribute -1 to the height, but this contribute +1. So in total, we get +2 height. So we have to insert a domino. So the 1, 2, 3. So this is U. So after U red monominos at the end, we're gonna insert a black domino. So we have to have board of size 2 larger. So these are just shifted because we insert something. But now we're gonna insert this. But what about the weight? Here the weight is lambda 3. The weight is minus lambda 3. This weight stays the same. So as you can see, now they change the sign like this. So it is a sign reversing involution actually. Oh, and this is case 1. And for case 2, is U greater than A. And this is really the same, so it's like this direction. You see, maybe this is U prime. U prime is 5. Here A prime is you see now U prime is bigger than this, just like this. Here U prime is bigger than this, so we can always go back in this way. And the remaining case is that so we covered this, but not the case that they are equal. So we have to write that down here. N equals U equals A. But again, in this case, this. In this case, they must all be equal. If you just think about them, they're all equal. So in this case, we define this to be itself. But in this is actually must be an element in Y. So sign reversing involution, weight preserving sign reversing involution that we wanted. So that'll prove that identity. Yeah, I didn't explain the full details, but I hope that you understand the idea here. If you think about them, and then you will be able to complete the proof. Yeah. So, in summary, we proved these two identities, completely combinatorially without assuming any knowledge in orthogonal polynomials or linear algebra. So you can just plug in any numbers in Bn, lambda, n because they are just arbitrary sequences. So in the next class, we will see some interesting special cases of this. and that will correspond to something that we already know, like the duality between Stirling numbers of the first kind and second kind, and the duality between elementary symmetric functions and complete homogeneous symmetric functions. Okay, so that's it for today. Thank you for your attention.